Hello, everyone, and welcome back to an Ozone Talks, part of the Pinnacle Academy, where we go beyond the theory, but we uncover the real science and engineering behind the systems and how the future is actually being developed in the next couple of years. Today, we're doing something special, something that has never been done before, but we want to provide you guys with this technical, in-depth conversations with one of our ozone systems and more in touch in the ozone generator itself, or the ozone cell. I'm joined by Eric Francis, the engineer behind our flagship Quadblock ozone cell, a patented design that has redefined performance, reliability, and efficiency in ozone generation. With over 30 years at PTI and Pinnacle, Eric has worked very closely with Bud Francis, a pioneer in ozone technology. Together, they have worked to help shape the whole new generation of how high performance ozone systems are made in not just municipal, industrial, but also mission critical applications. So welcome, Eric. I'm also joined by Deton Julius as well, who is a technician and a customer support specialist at Pinnacle Ozone Solutions, where he specializes in diagnostic, troubleshooting, and field service support with the ozone cell itself. He's currently pursuing a degree in electronics with a focus in high frequency and high voltage systems. So something that he works really closely with our ozone Quadblock as well. And he brings a strong technical fundamental on the practical science on how the cell actually works. So we'll be talking about the hardware, the logistics, how the system actually performs, the controllability, and what sets the Quadblock apart. So we'll dive into the conversation and we'll discuss how this is different to anything else that's on the market. Okay.
Thank you for that warm intro, Sannel. It's always let me tell you, yeah, the years they just fly by, but we're making new developments all the time, and it's really a blessing and a privilege working, like I say, with my father, Bud Francis. A lot of people. He's helped a lot of people over the years, and really, yeah, he's still going strong. So we're all benefiting from a lot of that ingenuity that he's brought to the table.
Yeah, totally agree with you. So let's jump into this conversation. What I want to do is I want to discuss, we have a few different segments, but I really do want to talk about the ozone cell in terms of efficiency, the energy used, the controllability, and the output. I think that's something that's very high demand, and I think our customers need to understand, our viewers need to understand why this is a critical aspect. So Eric, starting with you, in terms of performance, the Quadblock is often described as one of the most efficient ozone cells. What exactly contributes to the energy efficiency? What is the aspect behind that?
Well, yeah, basically, fundamentally, you got different operating principles going on. So from the front side electronics to the high voltage, all the way to the ozone cell, which is converting pure gas, oxygen gas into ozone. So all three of those need to work in concert together. So each one has been developed, with that in mind. Mm-hmm. The block, its fundamental design was from the parts that are chosen to the build quality all the way down to the final test. But the other X factor, maybe one of the most important variables is the people working on it too. And that's where, folks like Deton that shine, where we are able to really develop from within the personnel, but then also, give them opportunities, higher education, work, school, and studies like that, and develop some of those skills. And then a lot of these good ideas, they actually come from within, but it's really about the build quality and the quality of parts going in and how we can diagnostically approve them. And then are they even worthy to be built in a generator? And then, of course, now with some of the fundamentals and the foundation solid, then we can actually create the ozone.
Yeah, and so you spoke about controllability and you spoke about the modular design. Can you walk us through what type of precision, what type of turn down, what are we actually achieving with the Quadblock itself?
Well, what's really in the industry, there was a pent-up demand for that controllability, but so we implement PDM, pulse density modulation. So you can almost think of it that the electronics is taking, your normal wall mains, AC mains, and a microprocessor is managing an event, basically. Now it's sending out a square wave to the high voltage, but what it can do is basically chop up and create, on and off times, very linear. So that allows you to have a turn down control all the way to 10%. But then also, because it's a microprocessors involved, I mean, you can implement this in, very high resolution. Mm-hmm. So to have within, a turn down, it's nice to turn something down. But what's nice about, now you can implement that to an ORP or a PID, loop control. So you can interface with our electronics to really get that high precision level of linear control. And what's nice about the Pinnacle system is now you can not only manage the energy, but also the gas flow to provide more of a constant concentration approach. The application essentially is first. Like you can drive that very quickly because the linear response is very quick. The device is operating at high frequency. There's high voltage, but high frequency above 20 kilohertz.
Yeah, and I think that's something that we also touched in our previous conversation when we talked about the efficiencies and how optimizing water systems. But how do you see the efficiencies translating into cost savings? I think that's something that is tremendous, right? With the modular system and the energy savings that a customer has. No one really talks about the cost savings on the back end. Everyone just talks about cost of the capital equipment. But what type of savings do you see long term?
Well, yeah, because you essentially have a device that's operating more efficient, in the neighborhood of 3,800 watts per pound of ozone. So per day, I made it. So basically, that's the real-time rate. And now, because you could control the cooling, that even number even factors in the cooling aspect. So how much it costs you to cool down the unit. So just by sheer numbers, it is the most efficient. But what lends itself now, you can take advantage of that efficiency in two ways. You can either, because you're outputting so much more, you can have less equipment. But now it's nice to have a little more of a safety reserve aspect where if you need that extra ozone, now you can throttle up the unit and still meet your numbers at let's say on that specific job site, which would, but still doing that efficiently, which is, if the system is running for a 20-year life expectancy, I mean, you're going to recover the energy. I mean, electricity is not in general getting cheaper. So what that enables you to do is get a return on investment, much quicker. So, and usually, if you can avoid paying the power bill. Oh, another aspect which makes it efficient is its front end electronics too. So the way it interacts with the AC mains with bus compensation. So it's all about keeping the ozone stable. Mm-hmm. You got to have stability. I mean, without stability, then it wouldn't make it work in the application, where the ozone is being made.
Yeah. And so I know everyone talks about the ozone cell, but I don't know if Deton, if you could show us, or Eric, you could give me a little bit of understanding of the core technology being used in the Quadblock so people can understand how ozone is actually made and how it actually performs.
Well, yeah, what Deton was doing there is checking some thermals on the unit, and the unit is very, it's a thermal thoroughbred. It really, if you can control those temperatures, the electronics will last longer. But the ozone, basically, heat is the enemy. So it's a very, we're basically walking, I want to say a tightrope, because we're managing that thermal event. So you're not just creating ozone to destroy it, but basically, we can validate that on the bench. And obviously, maybe then can elaborate just on some of the temperature sensors being employed and even some of the safety mechanisms inherently designed into the electronics and our device, which make it a UL listed product.
Yeah, and
just like Eric was saying, there's multiple temp sensors on the unit, one that's looking at the block temp, one that's looking at, the IGBT temps, making sure that everything is staying below a threshold. That threshold is set, in the firmware on the board. If it starts getting too hot, it's going to start throttling stuff back. If it gets extremely hot, it'll actually put itself into a standby mode until it, cools down. and right along with what Eric was saying was just, multiple revisions on the cooling jacket design, on the cell design, anything that we can do, like he said, to not just kill the ozone that we're producing, trying to capture as much as we're producing rather than it dying to heat.
Yeah, and I know we speak about the warranty that Pinnacle provides, which is way greater than any other dielectrics. We give a 20-year warranty on the dielectrics. What actually sets the dielectrics apart from your convenient or your conventional ozone cells that are out there? Why that extended warranty? Why do we think that it's going to last even more than 20 years?
Well, yeah, my father always said we don't want to make boomerangs. So, I mean, we've tested and worked with our vendors very closely, and some of these vendors, we have multiple vendors, of course, but these are basically more or less kind of thought leaders in the industry. And when you ask them, you'd like more of a tailored blend, you're seeing this react to the ozone a certain way. And a lot of ozone is such a small sector, because there's a lot of applications for ceramic, but to work with some of the leading ceramic manufacturers, on the planet, and they have an interest in working with you to make your product better, it becomes a lot of synergy there, where we're really making some, like you say, parts that are dielectric. That's part of the recipe is the dielectric withstand. That's why we can warranty it, in harsh circumstances for 5 years, and basically, at full power. Some our equipment's meant to run 24/7, and it's got to be durable, and you got to be able to get uniform results with the ozone. So not only is the machining, the tolerance, and the blend of ceramics really second to none. I mean, it's got that, but it's got to be quality too. So that's one area where you really keyed in on a critical component, and I think that's the attention that we've spent in the research into our ceramic and how we manage the heat and how it interacts with the ozone, right where the ozone is created, is a very, that's a very critical part. So really they're all critical because it's really, a sum of parts, but we want predictable performance. We want quality incoming, so we have reliable performance outgoing.
Yeah, and I think that plays hand in hand with this. My follow-up question is, we talk about the interface and how it actually control, so let me take a step further back and say this. How do it actually integrate it with the interface with the ozone cell? Is there any feedback that plays crucial role in this ozone cell? Does it how do you figure out how the cell is performing?
Well, in some sense, that's where the microprocessor comes into play, and as Denton off his shoulder there, you'll see a computer monitor. So in-house, we developed and all this. It's the people again that make the difference, because in this geographical area, we work with some pretty high-level companies. And, through the years, we've developed quite a few relationships where they're experts in their field. So that's essentially a PlasmaView software, which we use diagnostically to qualify. It interrogates each, unit, and there's so it's communicating with the processor. So it's giving you numerical data. It has basically, these watchdog timers in it. It's looking for things. So that's just something we've developed for our own use. But really, we made that available to integrators and end users, so they could put that in there. They could use all those variables and all the numerical data and everything that's happening behind the scenes with our unit, all the sensors, all the bus voltages, all the critical information they can use, on their touchscreen panels. And I'm sure, and Pinnacle has taken full advantage of that to really make a very interactive system. I think one you can even monitor from your office. So that's really, and there's also primarily one is PlasmaView, but there's also another one we use, which is a wireless one, which even work on the smartphone, called PlasmaLink. But it's just all about bringing some new wrinkles into the equation, and how do you get people the information so they can make good decisions with, is my system running correctly? Am I getting the feedback? Is it another piece of ancillary equipment that's an issue? So it brings peace of mind when people have that extra information available, and they really know that this piece of equipment's operating the way it should. It's within parameters, and I can look elsewhere. So it's a nice, maybe, I don't know if that is any other thing to add to that, kind of some highlights of maybe the Plasma Link or Plasma View, what it enables, what it facilitates.
Right. Yeah. I mean, it gives you all kinds of digital data, like he was saying, so you can see kind of exactly how the cell is running, off that microprocessor. And Plasma View on the computer allows you, and so does Plasma Link, to even like graph and chart data, the power level, the PDN level, the bus current and voltage, the temperature over time. You can chart all that stuff and save it to look back later, or use it for trying to make the system maybe even run even better. So it gives you a lot of options there.
Thank you guys for sharing so much about the technology. I think that is a portion that not a lot of people actually understand, but I think this is definitely help people understand that there's multiple layers behind designing the ozone cell. It's not just about a piece of equipment and it's not going to perform well. It's about constantly improving and actually providing the best available to everyone. So I do want to move on to more of the hardware and modular approach that we have with the Quadblock. I think that's something that we've seen a tremendous change in not just the industry, but in customer thought pattern as well, is that how modular approach works to help with not just service, but the uptime. Well, how does the architecture affect like scalability, serviceability, and uptime? What are your preferences, or like what do you see in terms of that?
Well, the nice thing, there's, because of the smarts of the unit, and the design, I mean, there's obviously, we touch on efficiency, and it's really nice to have that. But what comes along is a safety element. So now you're keeping, everything, it's in its own world managing itself, but it's really because of the design of smart. So what that's going to allow you to do from the modular standpoint is to really control each one independently of each other. If you really had a control architecture, I mean, it was really unlimited how you can manage the device, and from flow rates, the actual plasma block, the quad block internal, now you're able to operate on different points of the curve simply by programming some inputs into the unit, and it'll just servo to what you need it to do. So it's not, we're not wasting that energy there, but then we've made it easier to control it from an energy standpoint. And that's really where now you have some system redundancy there. And that's going to basically, from a system pressure point of view, that's going to allow you to really, I guess, let's say we're not reinventing the wheel to some degree. I don't know, did I fully address that? Because what more or less Pinnacle does from a modularity point of view, for instance, is really they take full advantage of that. And from a skip platform, let's just say you had 4 units running at the same time, and what happens if one unit goes offline? The way our block is individually, everything's manifolded, and it's there's actually 4 ozone cells. Obviously, that's why it's called the quad. So, but let's just say it does raise its hand and say I have a problem, and it lets you know about the problem. And if someone's interpolating that data, then what it lends you to do is take a unit offline, and the remaining 3 units will pick up that off units. It'll pick up the slack, and you can still operate at the same performance level, because we built in some, it's a conservative design. We built in some headroom. I mean, these parts are meant to go the distance. I mean, there's, even since the inception of the company, I mean, there's equipment that's still out there running. And if it's a lot of it's important what's in front of the system, what's after the system. Obviously, you don't want to have water in the generator, and that's really where it's nice to have a nice ozone generator, right? Mm-hmm. Just a really electronic masterpiece. But you really got to have that supporting architecture around it to get the most out of that singular piece of equipment.
Yeah. And I think that's the critical point too, is right, serviceability. What helps is Pinnacle puts multiple of these quad blocks into an ozone generator system. So if one does go down, it's easy to pull one and change one out. I think we recorded it takes less than 15 minutes to actually replace one of these quad blocks. But the nice thing is, even if one block goes down, we have that room to amp all the others up to compensate for a down block. And that's in a very rare situation where that happens. But that still gives you the reliability that even in these mission critical systems that go out there, we have systems that are not going to be down because you have many of these quad blocks that are able to perform constantly at a high level. Even if one drops, another one can, or the rest of the set can hold the load. And I know, go ahead.
Oh, I was just going to maybe add to that, because kind of what makes it tick behind the scene, you could really throw some new variables at the unit, but what makes it basically tick, it's a self-resonant device. So it's seeking a resonant state. So it has the ability, if you change your pressures or your flow dramatically, something changed at the job site and you need to adjust things around it. It doesn't need a big, let's just say you don't have to start over from the quad block. It is going to basically adapt and adjust and auto tune. That's something maybe a little bit more of a deeper dive is how the resonance seeking circuit works. But it's essentially, it's a constant power device. Basically, it can recognize the change. It has feed forward routines, so it knows what things should be, and then when something changes, it has the ability to optimize, even though there's something entirely new, a new change. So that's kind of the nice about the digital age and our product. We've updated it over the years to really work with all the modern control equipment. So everything is, let's just say when we started off, it was like a black and white TV. For an analogy, I mean, we're dealing with, this is a full color, high definition TV. We're from the self, basically the unit. What really makes it tick is it has it's a resonance seeking device. So basically as conditions change around the unit and you need to tailor the unit to run at a specific job site, maybe the pressures or flows change, and maybe that normally would be maybe a big adjustment to some other electronics and systems, to make everything work and get the right dosing. But because the unit, we call it auto tune, it's basically a constant power device. So essentially it's basically has a feed forward routine, and it's actively learning and adjusting, and it basically wants to optimize for what you told it to run at power levels, but it's automatically adjusting frequency to optimize, even though the situation just changed. So it's literally doing that, as part of its feed forward routine, and it's basically adjusting itself, pretty quickly. As other things adjust, it can compensate essentially and stay online. The effort there was so if something dramatic happened, the unit just wouldn't shut off, and now you're not making any ozone. It basically has the smarts to figure out how to run under that new situation and maximize throughput, output, ozone.
Yeah, I totally understand. And I think that's like, if we had to say what sets the quad block apart, I think that's something that no other technology in terms of the ozone industry has. Is a block that thinks by itself, in a way is kind of thinking by itself and able to adapt to the scenario. Other ozone cells in the industry, you're basically looking at a vessel that you basically just pass air through it and creates electricity, and you have ozone. This is a cell that's actually thinking and makes those changes, because that's the most critical part, is right when you have reliability and you're looking at reliability over a long period of time, you want the cell to constantly update itself and make sure that it doesn't make these errors. So would you say that's like the main fundamental difference between what this cell has compared to the industry?
It's definitely an integral part of the, an overall solution that's part of that smart design. And probably Deton can attest to this. Just because they have units in the field, and let's just say we've simulated some things, or we've gotten, that also interfaces with customers, and they might give them some feedback that they saw this situation happen, and they may have data logged it, and they really mapped out all the variables, and we could see how our system reacts to that. But the nice thing about that smarts is you're able to, have existing equipment in the field, but then basically upgrade its firmware, it's operating, and now you have a unit, previous units are now right up to speed. It can handle those, just new challenges, something that may have actually, caused a fault, a problem before. It's now adapted to that, and it's right there in the processor, and it's not going to let it happen, and it'll ride through what could be a bad event. I mean, an example of that could be what happens if you have a power glitch. When I was just getting started in ozone, if you had a big power event happen and it sometimes that didn't go very well, even you lost power to your generator. I guess it looks like we've taken a proactive, steps in engineering from customer feedback and understanding our processes and understanding how the unit functions. Mm-hmm. So, things that would be a problem. I was just as an example, let's just say you lost power to a unit, back when we first started in those, even 20, 30 years ago, that was a big problem. The unit might not start up again and boot up, but now as things have becoming more sophisticated, we've kept up with the times. Basically, I guess that's us highlighting is, once again, listening to the customers, but upgrading the firmware. It offers a huge, not only does it make your system, it just makes it smarter. I think you kind of touched on that. It's a smart design and keeping it basically a long service life because of the smarts. You can upgrade the system, you upgrade the firmware, and now you're going to overcome maybe something that would have brought the system offline. It's all about keeping the system online, and when the conditions have improved, either thermal temperatures or the AC line condition is now stable, it's going to try again, and it's going to basically, that's one of the nice features of the unit is really unparalleled, uptime, because usually someone wants to buy an ozone generator, they want that ozone, they don't want to hear why it's not. We don't want to be the company making a product that, your product is holding back. We want it to be a reliable, really well thought out, engineered piece of equipment that basically we want to be the last one in that whole chain of events where it's like, why am I not making ozone? We want to. Like I said, though, it's been a development process. That is for sure didn't happen by accident. It's basically a cognizant decision where we're gonna solve some of these problems firsthand and just make a better unit. So our customer's life essentially is that much easier. Let them worry about the chemistry. Yeah.
You change it from why am I not making any ozone? So I didn't know I could make this much ozone.
Yeah, and I think this is a perfect segue, right? We're talking about listening to our customers. We're talking about how the cell has upgraded. I do want to spend some time. We can see this flow bench where Deton is standing. Can you explain a little bit? Can you show us a couple of things? What can our customers see or our listeners see from here, and that you can provide us so people get a better understanding about the ozone cell and actually what we do behind the scenes to help it get a better efficiency, better production, and get an overall better product at the end of the day?
Right. Okay. Yeah. So, this is the bench that pretty much every quad that we make here is going to go through, so from seasoning the unit in to getting the final test numbers, we're verifying all the board features, making sure that the features that Eric just talked about, are working and working properly. And then we go on to, running oxygen through many of these valves that you can see on the back wall there. So we're, flowing actual, 100% oxygen through the blocks. We're setting them to the appropriate power level and then verifying that, we're actually producing the ozone that we claim we produce. And I think Eric has talked about before that, they're kind of understated. There is that headroom there so that if something does happen to, one of the many units in one of these Pinnacle systems, that it can kind of pick up that slack. So yeah, we're just, go through, we verify all the features electronically, verify it's making, good ozone numbers. And then it can kind of be on its way. We do that thermal check like we showed kind of before, just to make sure that everything is thermally looking correct before it gets shipped out the door. So one of those, the customers kind of care about that quality, not necessarily where it's coming from,
Mm-hmm. Yeah, and I think that helps us with understanding the Quadblock technology. In terms of your guys' opinion, what do you see? What are your guys' next things that we can see on the block? What are you guys working on in the future? Like, what can we look at? I know this is Gen 4 now. What is Gen 5, 6, 7? What can we expect?
Right. Well, yeah, and what you see as a little montage of units, there's actually, even the Gen 2s are still pretty formidable. I mean, they're out running. Just there's plenty of those out there. And you can take notice even some of the physical appearance. We're looking at different alloys, different blends of material, and just making advancements there with obviously efficiency, reliability, and just durability. And so the other thing which we're really working on obviously is something called more or less like a plasma valve. Okay, and then what this could do is you're really creating the ozone, and you're really getting right at the atomic level. Like, basically, you don't want to waste a drop of it. Right? If we were in the bottled water, you just want everything to go in the bottom. But we want to convert as much as we can. All the way. But how you get there is really pushing the envelope. All the elastomers in the block, everything's got to hold up, because it's got to be, basically from. We don't want to disrupt the recipe, the foundation, which a lot of that core architecture is built on. So, but to some degree, we want to push the envelope a little bit, and that's all R&D. The same block, the quad block, is approaching near 30% weight. So that's a whole different dynamic to make it shine up there and to push the envelope. But that works its way backward. Some of that, I guess you'd say R&D, it ends up back into the production unit, and advancements are made from what was learned at those really high levels of ozone concentration. That ends up back to make it a better production project. The currently. So there's the other product sitting there is the Gen 4, and that represented a different topology inside. And essentially, that once again it utilizes. There's different alloys, there's different airflow strategies inside where the topology, where the gas is being created. It's really more of an emphasis on making the ozone and then getting it out of the ozone keeping that concentrated. So basically the next step is Gen 5, and there's, basically a 410, 400. Actually, I shouldn't say 410. It would be a DAT 410. Currently, that employs we call it a digital auto tune 210 series. So it's really running at 240. But in development, we already have the transformers developed and a DAT 410, which is under UL accreditation. It's under that process. So that's going to be called our DAT 410. So now you're going to be able to operate anywhere between 380 volts and 480 volts, basically. So more an industrial voltage. So that, but then again, it'll carry the same type of ratings. And ultimately the cell, it would be, that's going to be the next Gen 5, where we're going to, like I say, work in some of these, anything from you might see upcoming in the future, a plasma valve, or, essentially basically a different flow strategy inside to really, let's say, up the concentration. Right now there's a very nice, they're optimized for 10 to 12% weight, but, this different topology and really, we're commanding the gas different. And basically that would lend itself upwards of, almost a 60% improvement in performance. So that's really where we're talking now, in that same physical shape too. So we're, the same physical limitations, the same structure. We're talking about getting that much gas,
Wow.
and production out of it, because we can the electronics have already been developed, and then the high voltage magnetics, and now the final piece of that puzzle is now we can get more energy into the cell. We can get the heat out of the cell. So that would be all those changes I just was talking about. That would encompass a new generation. So that for the company to make a new generation of product, it has to be more of a substantial shift. And just the shift in performance is nice, picking up more ozone out of the same physical package, but really having the ability to make higher levels of concentration if needed, which some applications are going that direction. But then all what people are accustomed to with the smart electronics and the safety aspect, where the pressure and electrical hazards. Basically, that's what we've done there with the top enclosure is made a device that's you're not going to get shocked on. And it's very quiet too, audibly, like in that room that ends in. Usually the fans are the loudest aspect of the ozone generation, and it's a clean, it's very eloquent actually, the way the electronics are working. We're not contributing to a lot of noise and hash on people's power lines. So the device is from that aspect very, it's pretty quiet. I mean, there's Lloyd's testing, so it's very durable. In the marine environment, it's designed to take, if you're familiar with the Lloyd's testing, they're basically shaking it on a shake table, really trying to find any weaknesses there. So we obviously the device is capable of that, but then just putting it in an environment where it's not contributing to a bunch of noise. Because let me tell you, I mean, let's just say you wouldn't want something with that much power and energy to start to make bad decisions and get mixed up. There's a methodology to it. The design, it has a designer, and it's just very robust.
Yeah, no, I think after this whole conversations, our listeners are probably asking one question: what is the specs on the ozone cell on the Quadblock? Can you basically walk us through what is required, like inlet outlet flows, pressures, and what type of ozone production can we expect in terms of not just the grams per hour, but also the percentage coming out of the cells?
Sure. Right. Yeah. Den probably knows the numbers by heart to make the 10%. I mean, it's right. We do things on a mass airflow, which is, right in the neighborhood of like 43 standard liters a minute, but he could probably elaborate on the exact power levels and, your ozone concentration as the ozone analyzers indicate. They're really, things are optimized. We go for a 10% spec. That's which you should be in the neighborhood of, what does it sound like, anywhere between 360. I mean, if you push the cooling water, you could eclipse that. Does that sound reasonable then?
Oh yeah, definitely. Everything, like you said, that runs through the lab, we're looking to make sure that it makes that 10% number. If it makes that 10% number at the flow rate that we're expecting, 20 psi of oxygen going in, then we know that it's going to be able to be adjusted the way that it needs to be in order to make, the other numbers that people might be looking for concentration wise. Eric mentioned before that it can get into the mid 20% concentration. But we're looking for, around 360 grams at 10%, 20 psi, around 43 standard liters per minute.
Okay.
And then, and 2,800 watts at the being measured, and that's three phase. So you got 243 phase, 2,800 watts is a real nice operating point for the block. Basically, that's it does a good job. Basically 65 degree water, and some people run their cells at 50 degree water on average. If you do that, you take our number there that Deton just outlined. You give it, you improve the cooling water down to 50 degrees. You picked up another pound of ozone. And that's nice to do. If somebody, let's just say they had a situation, the process first mentality at the job site, they need some more ozone out of the unit. Our unit will certainly, it's up to the task. It can deliver more. We don't want to oversell the ozone. They want to make it's on 24/7. it's the measurement is taken at an operating temperature. So this is when you run your unit in the field, you would expect that number. I mean, unless you're perhaps giving it a bad quality of gas, for instance, or what happens if something the gas isn't getting to the unit, but that pretty rare these days because of the sophistication with all the ancillary controls around the unit are help managing the whole ozone delivery.
And let's talk about that before we end or wrap this up. What I want to discuss is, like, in terms of the ozone cell itself, like we talked about power. Power is required for the cell. We talked about cooling water. Cooling water is required. We talked about oxygen. We have either you can use LOX or you can use PSA or VSA units, and then the ozone comes out of there. Is there any other parameters that you see as issues or things that our customer need to be worried about? Or in terms of the ozone cell itself, is there what other requirements are needed for that cell to perform?
Well, yeah, you hit the nail on the head with the gas quality is paramount. I mean, it's just say the old, good input in, right? Good input out. So your gas quality really needs to be better than 93% if you want to make anywhere near 10% concentration by weight. So, you do. And the other unique feature about the way our metallurgy and some of the, I guess you'd say, even some of the coatings that are employed inside is you don't need to add any kind of nitrogen into the equation. It can operate on medical grade, and some people do. We have products all over the world where they operate on, they want purity of that gas. And we've made units in the medical realm where our unit doesn't suffer from an oxygen poisoning. That phenomena that's been from the ground up, it was developed so that wouldn't be an issue, because it's just ultimately people spend a lot of money on gas prep, but it's really our unit relies on good gas quality. So if someone's monitoring the purity, I mean, that's always essential to know how good the gas is and the dew point. But even some of the materials in when the going gets tough and some of the conditions are a little subpar, that doesn't mean our unit's going to definitely arc out. While it's going to become more demanding, the unit has the ability to, let's say, tune around some of those adversities. So it's going to adjust to the frequency actively. And, let's just say it does, the environment inside the ozone cell are more conducive to something bad happening. It can start to put on the brakes and save itself. So basically the processor is in charge of some of those. So even as adversity occurs, it can actually still operate in sub-ideal circumstances.
Okay. All right. So thank you guys so much for the information that you've provided. I do want to ask you guys a very critical question here. Is if you had to give one piece of advice to a young engineer or someone that's actually working on the gas phase technology, especially in ozone, what advice would you give them? So Eric, starting with you and then over to you, Deton.
Boy, that almost sounds a little like a loaded question, but you could get into the aspect of don't let your education get in the way of your learning, because the way some of these technologies intersect, and really determining what's the critical variable, because you could spend a lot of time trying to make a very small improvement, but kind of thinking outside the box is all, that there's always that cliche, but I think it's just, how that information is applied, and just because it's, I mean, on the forefront of ozone, and you mentioned that to like a lot of different people, and they assume it's the ozone layer, and you're doing something with weather balloons up in the stratosphere or something. So when it comes down to just applying what's learning and applying that, it seems like that would be just going back to the fundamental and making those small improvements. But sometimes putting forth that effort is just critical, because it actually it might reveal something you may have never even considered before, and all of a sudden you're able to open the door into a new area of a arena, basically, that a door opens, which you probably never would have got to that final step in fixing the initial problem. You actually solved multiple things, but you did, kind of the law of unintended consequences. Mm-hmm. Be ready for unintended things, I guess. But just keep fresh eyes on on a solution. It seems like, because it's easy to kind of get mired down and then discouraged, or it's really exciting, you're part of something, an organization, that's exciting. There's all these different dynamics, but the core engineering, it really takes precedence. So it's really nice, working at an organization that spends a lot of money on R&D and it's focused on that, because there's value to it inherently, but it's really, once again, there's people making it happen, and you really want to be in a place that's going to nurture that and really develop it. And I think that's the product really shows, because of that mentality, from the onset. But that's where I was at the beginning. It was just really benefited, and it's really a privilege being around people like that in an organization. So
yeah, thank you. Deton, over to you. Any advice that you would give?
Yeah, I would just say to not stop learning. I've been here for 10 years now, and there's a lot of stuff that I definitely learned in school, individual electronic stuff. But once you get into the industry, like the ozone side of stuff, the gas glove side of stuff, the physics side of stuff, some of that stuff you might not necessarily learn, in school. So just keep pushing to learn even more. There's a ton of stuff that I learned from Bud and Eric that I don't know that I ever would have learned in school. Yeah. So that's my main thing, is just keep pushing to learn something new every single day.
Yeah, perfect. All right. Thank you, Eric. Thank you, Deton, for having this incredible conversation. This has been an incredible deep dive. I know our viewers, especially our technical audience, would take a ton of information away from this. And for those who are watching Pinnacle Academy, we'll continue to host discussions like this, combining not just what we have in the field, but in-depth innovation about engineering, about leadership. We want to try to elevate not just ozone, but the water industry in itself. So thank you, everyone, for joining us. Be sure to follow us on YouTube, LinkedIn, and any future videos that we do take out. Thank you again for joining us. Thank you, guys.
You're welcome.
Thank you.
My pleasure.
Take care.